Hello, welcome to this week's Naked Scientists with me, Chris Smith, and also with Dominic Ford. Hello, Dominic.
Hello, and this week, how nuclear bombs have helped to prove that adults make new brain cells. Is Michael Douglas right when he says his oral cancer was caused by a virus? And GPS spoofing. Can your sat-nav be tricked into telling you you're somewhere you're not?
And if you'd like to find out how you can get in touch with us here at The Naked Scientists, there's no doubt about that. Email chris@thenakedscientist.com, tweet @nakedscientists, or look us up on our Facebook page.
The Naked Scientists podcast is powered by ukfast.co.uk.
Let's kick off with a look at this week's science news headlines, as ever. And first up, there's evidence now that the question of whether human adults can make new brain cells and use those brain cells appears to have been resolved. And that has been done using, would you believe it, nuclear bomb tests from the Cold War era. This is the work of Kirsty Spalding. She's a researcher at the Karolinska Institute in Sweden. It's published this week in the journal Cell. And what she and her team have been developing over the last about 10 years is a way of carbon dating cells using carbon which is in the DNA in those cells. So what she has done is to get samples of brain tissue from people aged between 19 and 92. You extract the DNA from those cells, and because when people are eating food, and that food has been grown from plants, which is taking carbon dioxide out of the atmosphere, the amount of radioactive carbon in the form of carbon dioxide in the atmosphere ultimately ends up in that person. Now, if nerve cells are only born in a person when they are themselves born, in other words, one person's set of brain cells has to last a lifetime, then the amount of radioactive carbon-14 should be equivalent to what was in the atmosphere at the time when that person was born. If, on the other hand, they're making new nerve cells during their lifetime, then they're going to put in a carbon signature equivalent to what is in the atmosphere at the time they make those new nerve cells, because they're eating food that's just been produced. And they can actually carbon date cells to within 1.5 years of their real age. Magically, what they find is that there is clear evidence that the hippocampus, the part of the brain on each side which is concerned with memory, is turning over cells at the rate of 700 new nerve cells being born every day and wired into the brain. So over a year, that adds up to a replacement of roughly 2% of your hippocampus cells, and over a lifetime, a third of the brain cells actually become replaced over your lifetime with newborn nerve cells. And this shows that the adult brain clearly can make new nerve cells, they wire themselves in, and they're functional.
And how did these nuclear bombs help them to discover that?
Well, because the nuclear tests in the Cold War era in the 1950s and the 1960s led to the ejection into the atmosphere of large amounts of radioactive material, including radiocarbon, it raised the overall amount of radioactive carbon dioxide in the atmosphere, and there's a blip on the atmospheric radiocarbon graph, which would have been taken in by plants and then fed into animals and ultimately through the food chain ended up in people and is mirrored in these people's DNA.
It's interesting that we're making these new cells even in adult life, because we talk about how it's much easier to learn a new language when you're a young kid and so forth.
They and others have been looking at this issue because originally the dogma was the brain doesn't make new nerve cells. And this is part of the reason why we get degenerative brain diseases. But then in the late 90s, researchers in several countries realised that the brain can make new nerve cells, not everywhere, but in some discrete places. But then critics said they probably don't do anything, they probably don't survive, they just die off. So the question has been, well, do they actually do anything? And if they do, how long do they live for? This study shows that they're not living as long as your own normal brain cells. Maybe they live 10 times less long, but they nonetheless live a fairly long time, and they clearly are wiring themselves in and contributing in relation to memory. And they say that needs to be studied next, because perhaps these cells are involved in storing new memories.
So perhaps it is actually possible to teach an old dog new tricks. Now, I spotted a paper this week in Science which is looking at how we study the upper atmosphere of the sun, which is an interesting environment because it's so very different from any environments that we are used to on Earth. It's incredibly hot, it's at about 6,000 degrees centigrade, and you've got incredibly strong magnetic field coming out of the sun, which are creating at times violent explosions where the sun ejects vast quantities of material out into the solar system. And we would really like to understand that environment better For example, nuclear fusion, the process the sun uses to power itself, is something we could use on Earth potentially for power stations of the future to solve our energy crisis.
Haven't we got telescopes to look at the sun with then?
So we do have telescopes, but if you look from the Earth, you just see this two-dimensional image of the structure of the material there. And what you really want is to understand those structures in 3 dimensions and to understand what the magnetic fields are doing. And those you can't see because they don't produce any light. So what we would like to do would be to put a test particle there and see how it behaves in this environment. But getting there is very difficult. Now, a couple of years ago in 2011, Nature actually, by good luck, provided us with just such a particle because Comet 2011 W3 Lovejoy actually passed very close to the Sun. It was actually skimming through its atmosphere. And writing in Science this week, Cooper Downs of the Predictive Science Institute in San Diego actually took observations of Comet Lovejoy's path through that atmosphere. It was leaving a trail of steam behind it, and he was looking at that material and watching it how it was changing in response to the magnetic fields and the heat that it was experiencing. And from that, he was able to produce quite a detailed model of both magnetism and heat. And that actually really helps us to understand the environment around the sun and potentially what's triggering these huge explosions that occasionally mean that the sun throw out vast quantities of material into the solar system.
And what did he learn from watching the comet go on this sort of surface skimming approach to the sun?
There's a lot of work to be done in understanding the sun, because what we would really love to be able to do is to make fusion reactions on Earth that create energy in much the same way that the sun creates energy. And that's a very difficult problem because magnetism is a force that it's very difficult to understand. But what we have now is data along this line that the comet traversed of what the environment was, and that helps us to build better models of how the sun behaves.
Thanks, Dominic. We're here back on Earth for a minute. This week, the actor Michael Douglas revealed in an interview with The Guardian, rather than The Sun newspaper, that he believes the throat cancer he suffered was as a result of infection with the human papillomavirus, that's HPV, an infection that he believes he contracted through oral sex. Dominic teamed up with Kate Lamble to bring you the quick-fire science.
Human papillomavirus, or HPV, is the name of a group of more than 100 viruses which infect the skin and the membranes lining your body, like the inside of your mouth or the anogenital tract.
The virus is passed from person to person by skin to skin or genital contact.
More than half of men and women catch HPV within 3 years of becoming sexually active, and most will be unaware they've contracted it because in the majority of cases there are few, if any, symptoms.
An HPV infection will clear up easily in over 90% of cases, but some people will experience a persistent infection, which could put patients at risk of cancer throughout their lifetime.
15 HPV viruses are associated with an increased cancer risk. One type, HPV 16, is responsible for around 80% of anal cancers and 60% of oral cancers.
As well as their links with cancers, different members of the HPV family of viruses also cause warts and verrucas.
In the US, cases of throat cancers associated with HPV infection increased threefold between 1988 and 2004.
In the UK, an HPV vaccine has been offered to girls since 2008, but it is currently not offered to boys.
This is because we rely on the idea that immunised girls will protect the boys. However, critics argue that men who have sex with other men or unimmunised women are still at risk. Australia recently became one of the first countries to introduce the vaccine for both sexes.
We don't know whether Michael Douglas's oral cancer was HPV positive or negative, but the virus can be a factor in similar cases. To reduce the risk, doctors advise people to receive the HPV vaccine or use condoms or dental dams to reduce genital contact. Kate Lamble joining me for this week's Quickfire Science, which you can also download separately as its own podcast from our website, nakedscientist.com/quickfirescience.
Thanks, Dominic. More news now, and Phil Broadwith from Chemistry World magazine is with us. Phil, you got some news on a cluster of cases of something resembling Parkinson's disease around Mount Etna.
Yes, Chris, this is a story that the manganese from the surface of the rocks that are spewed out by the volcano when it erupts may be contaminating the environment, and manganese poisoning has very similar symptoms to Parkinson's disease. So it may well be that what has been diagnosed as Parkinson's disease is actually manganism.
Are there lots of people in that area then with Parkinson's-like symptoms?
Yes, the incidence of Parkinson's disease is above average, and that's something that's been puzzling doctors for a little while. There have been tests of the water supply around there, and that's found that there is a lot of manganese, around 2,600 micrograms per litre, where the safe limit set by the Italian government is about 50 micrograms per litre.
So they think they're getting it in the water?
Probably, but what wasn't really known before is how it gets into the water. And the rocks from the lava had been more or less discounted because the manganese concentration wasn't high enough.
What, so if you take a piece of rock and grind it up and say how much manganese is in here, it doesn't look like there's very much. Is that what you're saying?
Yeah, absolutely.
So where's it coming from then?
Well, what Antonino Giulino and his colleagues at the University of Catania, which is just in the shadow of Etna, have done is look at the surface of the lava rocks. And it turns out that manganese and a few other elements actually segregate onto the surface of the lava rather than they're not evenly distributed throughout the bulk of the rocks. So if you grind them up or do a bulk technique, you're not going to see that higher manganese concentration.
And do they think that the manganese washes off of the rock surface in that case into the local drinking water?
Well, because it's on the surface, that's the part that gets weathered away. It's the part that is more in contact with the environment. So it's much more likely that you could see higher manganese leaching off out of the soil into the groundwater.
And is everyone vulnerable to this manganism? I've never heard of it.
As far as I know, everybody's body has the same chemistry more or less, so everybody's pretty much vulnerable to, if you have high concentrations of manganese, you can end up with this neurodegenerative symptoms. And
can they test for it?
I'm not sure whether you can test to see exactly whether a specific person's symptoms have been caused by manganese or just by other forms of Parkinson's disease, but you could certainly test whether they have high levels of manganese in their body, and that would be some kind of correlation.
What are they recommending for the people around Etna drinking bottled water then?
Well, there are things that you could do to sort of filter the water as it enters into the groundwater system. There are ways of removing manganese from groundwater, so that would be a good first step.
Thanks very much, Phil. That's Phil Broadwith. He's from Chemistry World magazine. Dominic, how planets form?
That's right. I mean, I guess this is a question that people have been wondering about for as long as they've been looking at the night sky, how the Earth and planets in the solar system formed. And the ideas that theorists have come up with in recent decades is that the whole solar system formed out of a gas cloud which collapsed under its own gravity, and the central part of that will have formed into the sun. And then there will have been some material around that which was less tightly gravitationally bound, which formed a system of planets around it. But a paper in Science this week by Nienke van der Marel from the Leiden Observatory looks at a problem with that model, which is that if you were to have material in this disk around the young sun, and you thought about how that might collapse down to form planets, you'd start to have rocks that would conglomerate together, and then those would collide with one another and perhaps stick together to form bigger bodies and eventually build up to form something Earth-like. But if you think about what happens when you go to the beach and you throw two rocks at one another, they don't tend to stick together, they tend to fragment into pieces. So that's one rather large problem with this model. The other problem is that as these bodies start to conglomerate together, they're feeling friction from the disk around them, and that friction tends to mean they lose their orbital
orbital down,
speed.
aren't they?
They're going to slow down, they're going to spiral in towards the sun.
So why don't they?
In fact, this is rather fascinating because we don't understand very well how the planets of the solar system could possibly have formed. And the best idea that people have had is that these solid particles that were coming together to form the planets perhaps were attracted by gravity before they stuck together. So you had a swarm of dust particles that weren't actually stuck together but were just gravitationally
sort of
attracted. Loosely associated swarm of dust particles orbiting around the sun that eventually came together and stuck. But it's been really challenging to actually make observations to see if this model stands up, because if you look at stars around the sun, you try and look at planets forming around them. These are so very close to this very bright object, it's virtually impossible to make that observation until the last year, because the Atacama Large Millimetre Array, or ALMA, has just come online in Chile. It's actually only half built, but it's already taking scientific observations. And it's observed a nearby star, and it's looked at this disk of material around that star, and what it's seen is an asymmetry with this clump of material apparently on one side of that star. And this looks very like what you'd expect from this model, where planets form out of these swarms of dust, which eventually then stick, but to begin with, are just bound by gravity.
Is there not something sort of similar going on in the ring system of, say, Saturn that could teach us a bit about this? Because that must be similar physics.
It's similar physics, but it's a bit different. The rings of Saturn, I guess it's an age-old question, why don't the rings of Saturn just form into a moon, given all the other material did form into moons? And the answer seems to be that they're so very close to Saturn that they feel quite a disruptive, what's called a tidal gravitational pull from Saturn itself, and that actually stops them from coming together under their own self-gravity.
So now do we need to just go and find some other examples to test this, because it's still just one observation?
Yes, that's right. And ALMA is a very young telescope. As I say, it's not actually finished yet, and it's going to be with us for decades to come. So I think this is the first very exciting result, but we can expect to see much more in coming years.
Well, finally, what is in a name? Turns out that parents are subconsciously selecting names that linguistically portray their children as, in the case of boys, masculine and stronger, and in the case of girls, much more feminine and petite. Now, let me explain. This is something called sound symbolism. Now, studies in nature have shown that if you look at an animal that wants to be friendly, it tends to make noises which have a higher pitch to them. So whines and bleats tend to be a sign of friendliness, whereas low-frequency, harsher noises tend to signify aggression, so a growl or a bark. They tend to say, I'm big, because big creatures tend to make lower frequency sounds. So animals definitely use this. Do humans? Well, if you play sounds from people and, say, take voices that are lower, and they tend to be dominated by low frequencies, back of the throat type noises, people interpret those as coming from someone who is more masculine, more testosterone charged, and probably with bigger body strength than someone who has a higher voice. So it does appear that this sort of works in humans, but how does this apply to the names we give kids? Because if you think about it, some names, you have to use lower pitch sounds to make those names than other names. So if I take the name Michael, for example, Michael, you have to make the sound towards the back of your mouth, the my bit, and it tends to push the frequency down. Whereas Michelle, the girl equivalent, you tend to bring that to the front of your mouth, and it's a higher pitch. So does this apply? Well, there's a paper in PLOS One this week. Alan McElligott and his colleagues at Queen Mary University of London have tested this. They got the most popular boys and girls names from US, UK and Australia, New South Wales, and they asked, in these most popular names, are we seeing preferentially boys' names that tend to have these vowels which are low frequencies up front in the word, the dominant sound, and girls' names with a higher pitch? There is a really statistically significant association between sounds that are high-pitched versus sounds that are low-pitched, girls versus boys. Phil?
It'd be interesting to see if that works in other languages as well, because all of those are English language-speaking nations. So has it looked at other languages?
I spoke to Alan McElligott about this, and he says, very interesting question, they don't know yet, but he does have some interesting examples, which are that they may expect the precise opposite to happen in other languages, because, for instance, if you look in African cultures, whereas in Britain we tend to, or in Western cultures, slim, short women are regarded as the ideal. In African cultures, you want a woman who's extremely well fed because this is a sign of health and riches. So actually, it may be that if you look in those particular cultures, you're going to find people who have actually low pitch type names signifying large, because that's actually what you want. So you may find the counter-argument is also true. So they're actually going to do that study next.
We had quite an interesting conversation in the office earlier about whether our names were masculine or feminine, and I think mine seems to obey the rules because, Dominic, the O is a masculine sound, but we thought yours, Chris, actually, that I is actually not very masculine. But if you take your full name, Christopher, the offer, that's more masculine. So in fact, your full name, Chris, is masculine, but the abbreviation we're not so sure about.
I better stick to the long version of the name then. Well, they opened the paper by saying James Bond. And James is a bit like Chris. It's quite high-pitched, but the Bond gives you the lower O. And so that Ian Fleming presumably chose that phlegmatic character very much on purpose. Now, I'm sure we've all found ourselves eating ice cream directly out of the tub at times of great stress, but a new study out this week suggests that people who are mildly depressed lose the ability to distinguish different levels of fat in foods. Paul Breslin is from Rutgers University, New Jersey, and the Monell Chemical Senses Lab in Philadelphia. He's with us now. Hello, Paul.
Hello.
First of all, how do we actually taste fat? Because you put something in your mouth and you say that tastes sweet or bitter, but what's the taste of fat?
Fat is largely experienced as a feeling on the skin inside the mouth. So if you put a drop of oil on your fingertips and rub them together, you can tell that there's fat there because it's slippery. And we would feel it the same way in the mouth. It has to do with lubrication of the inside of the oral cavity and everything moving around in there. In addition to that, there's also receptors for fats on taste cells. And we don't know exactly what they're doing yet, but they're probably participating in the perception of any kind of food fat that we would be perceiving.
So when you began this study, what was the hypothesis that you were pursuing here?
So the idea is that we know that we can manipulate our body's chemistry, in particular our brain chemistry, either by taking drugs that manipulate the chemistry or through stress, anxiety, depression, or mood, and that they all have an impact on this. It's been observed that certain drugs in certain states can impact taste, and what we wanted to be able to do is to look at the impact of mood manipulation, manipulating the emotions of people with video clips that were happy or sad, on people who were very mildly subclinically either depressed or anxious, and see what the impact would be on their ability to perceive a variety of different stimuli in the mouth. And that would include things that taste bitter, sweet, salty, sour, as well as fats that were basically dairy cream. So taking heavy cream and diluting it down with skim milk, so you have a whole range of levels of fattiness and creaminess to perceive.
Sounds disappointing if you like your creme brulee. Why should a person find that their taste sensations are affected by mood?
The chemicals that are involved with how neurons in the brain talk to each other are also how the taste receptor cells and various cells in the mouth communicate with neurons that send signals to the brain letting you know what's in your mouth. So the cells talk to each other with these molecules. And when you have a manipulation of mood or state, you can actually manipulate those chemicals. So we know that there are certain classes of compounds involved with depression or anxiety, chemicals like serotonin or noradrenaline, and that the same things that have to do with affecting how you feel when you're depressed or how you feel when you're anxious, that have to do with the neurons communicating with each other in the brain, also have to do with how the cells that are responsible for our tasting what comes in the mouth talk to these neurons. So in principle, you should be able to manipulate someone's mood, say, and alter the chemicals not only that make them happy or sad from manipulating their brain chemistry, but simultaneously affect the chemicals in the mouth that affect how your taste receptor cells talk to those neurons.
And what did you find when you did that?
So there's an observation that other people have made that people who tend to be anxious or people who are depressed clinically, when you ask them how they perceive various tastes in the mouth, bitters, sweets, sours, salts, they tend to rate them higher. In fact, people who are anxious have a tendency to rate most stimuli higher. Things seem brighter or louder when they're anxious, and tastes also seem stronger. That also tends to be true for people who are depressed. It's also been shown that when you administer drugs, pharmaceuticals that manipulate these same systems, that you can acutely and reversibly make these tastes seem stronger as well. So we were experimentally taking people with very mild subclinical depression or anxiety. These weren't clinically depressed or anxious people. And we were manipulating their mood by showing them movie clips that were very happy or very sad clips or neutral, boring ones. And by doing that, we were trying to manipulate their chemistry and show that we could make these tastes stronger. We happened to also give them fats to evaluate, and it was not really known what would happen under those circumstances. Fats, it turns out, go the other way. When you manipulate mood by giving people these happy or sad video clips, if they're mildly subclinically depressed, they become worse at being able to distinguish between levels of fat in a cream.
Do you think that's significant in the sense that if someone is depressed, they're not going to care whether they watch their weight or eat a healthy diet?
Well, there are a couple associations that have been known. from studies of people in the past. One is that folks who are obese tend to have negative emotions, and people with negative emotions have a tendency to overeat. We also know that people who are obese have a tendency to underestimate fat levels in food and their fat intake. And we also know that people who have a higher body mass tend to be low in their sensitivity to fat. Those are all just observations. We were experimentally manipulating the system and really sort of showing that what those observations that had been made in the past were really making sense. And what it suggests is that perhaps people who tend to be heavier, have a higher body mass, tends to be slightly more depressed or have more negative affect. This tends to affect their ability to perceive fat, so that if they're eating something that were, say, high fat, they might not be able to know that it was high fat relative to something that were like a skim milk that had very little fat in it. And if they did that and weren't paying attention to how much fat they're eating, it could in fact make their body mass go up, which would put them into sort of a positive spiral of being heavier and having more troubles as a consequence of that.
And equally, people who become depressed, yes, there may be some motivational factors, but also they could end up eating more than they think they are, fat intake that is, and that would translate into a weight gain, which could then become self-fulfilling.
Yeah, the problem with this is that if you're not paying attention to what you're eating, you already have a predisposition to overeat. And if you're not aware of how much fat you're eating, then there's the cycle of obesity going up, negative emotions going up, overeating, and inattentiveness or inability to perceive fat level going up, and on it would go.
Paul, thank you very much. That's Paul Breslin. He is from Rutgers University and also the Monell Chemical Senses Lab in Philadelphia, and he published that work this week in the journal PLOS One.
You're listening to The Naked Scientist with Chris Smith and with me, Dominic Ford. We've all become used to using GPS sat-nav units in cars and on phones, which can pinpoint where we are. But now computer scientists have shown how people could fool these systems into lying about their location. Marcus Kuhn from the Computer Laboratory at Cambridge University works on what's called GPS spoofing. Now, Marcus, first of all, we're used to these sat-nav systems in our car, but how do they actually work out where we are?
So there are 24 satellites in an Earth orbit, and they're basically a bit like a speaking clock. They tell us all the time very precisely within a nanosecond what the time is, and they also tell us at the same time where exactly within a meter they are located. And if you know yourself what the time is, you can find out how much the signal has been delayed. From that you can calculate how far away you are from the satellites. And then if you know how far away you are from 3 satellites, you can intersect 3 spheres and know where you are. If you don't know the precise time, you need a 4th satellite to resolve the ambiguity. And this way you can calculate by looking at 4 satellites precisely what's your time and what's your location.
So it's a process of triangulation by knowing your distances from 3 or 4 satellites above your heads. Now, how maliciously can you go about tricking that system?
So the GPS signal consists actually of 2 signals. There is a signal exclusively reserved for the US military, and there is a public signal. And that public signal makes it possible for all of us to enjoy it in our smartphones, in our sat-navs. However, the signal is highly predictable. I know in advance what these satellites are going to broadcast over the next couple of hours. That makes it possible for me to receive it, but that also makes it possible for me to synthesize one of these signals. So I can build a device that creates a fake signal, and I can send it out, and I can make a GPS receiver believe that it's actually somewhere else or at a different time.
So if we take a practical example, we've got cars going past outside the window. If I wanted to trick a sat-nav in one of those cars into saying it was somewhere other than where it is, how could I do that?
You could send out a signal, but the particular applications that I'm worried about are not so much satellite receivers that are elsewhere. There are other applications where the person who owns the satellite receiver may have an incentive in that receiver showing a wrong result because the receiver doesn't quite work in their interest. So there are systems where a car insurance company gives you a satellite receiver and they charge you an insurance fee based on when and where you have been driving. There are lorry fleet management systems where an employer monitors the performance of their drivers, whether they are speeding, whether they are taking unauthorized detours, by looking at data from their satellite receivers. And in those situations, it's very tempting for the people who have control over the receiver to just disconnect the antenna and connect instead a little box that creates a spoof signal and makes the receiver believe it's elsewhere.
So what you're saying is if I hire a car and I know where that GPS receiver is in the car, I would disconnect the antenna. It wouldn't see the real satellites. If I had a computer next to me that was generating a fake signal, I could then pipe that into that receiver and make it think it was somewhere entirely different.
This may initially sound a bit far-fetched, but we have already seen quite a lot of manipulation in a similar older system, tachographs in lorries, which record how fast someone has been driving. And police have recovered from lorries little devices inserted into the line between the gearbox sensor and the tachograph, where with the remote control key fob, a lorry driver can easily reduce the speed by 10%, by 20%, or simulating a brake such that the record is faked. And one worry is that over time, as the technology for simulating these signals becomes simpler and cheaper, the same thing will be happening with GPS-based systems.
So what's your aim in researching techniques like this? Because I'm guessing at the computer laboratory, your job isn't to find tricks that people can use to basically do insurance fraud.
So as security researchers, we see our job in anticipating what sort of problems there will be in a couple of years' time. And this is important because the innovation with something as big as a satellite navigation system doesn't happen very quickly. These satellites last a bit over 10 years and they have to be replaced over 10 years. And it takes a long time to develop them. So if you want to make a modification to how the system works, you basically have to start thinking about this already 15 years into the future. And by that time, there may be a lot of applications that rely on these signals. And the signals at the moment are not designed really for security applications.
And how could we go about making this more secure? Would it involve people going out and buying new sat-nav units and replacing satellites?
So there are already a couple of techniques that can be used today, but they are mostly used in military systems. You can have not just a single antenna, but you can have several antennas in your GPS receiver. And that allows you also to find out from which direction the signals come. And if there is someone trying to jam you or trying to confuse you with a spoof fake signal, you just ignore them and you stick to the directions where you expect the signal to come from the satellites. That isn't really practical in consumer electronics where everything has to be very cheap. You don't have space for more than one antenna in your smartphone, or it would be expensive to fit 8 separate antennas around your car. So what we're looking at is adding additional information to next generation satellite signals. And at the moment, these signals are highly predictable. One technique is that you create a little bit of unpredictability, that you send out data that changes randomly, and then you can use technologies like digital signatures to verify that this unpredictable data was indeed correct, and also that it arrived exactly at the time at which you expected it. One difficulty with satellite navigation signals is they consist of two things. They consist of data that's being broadcast about where the satellites are at the moment, and you can use cryptography, digital signatures, in order to protect that data such that it can't easily be faked. However, in navigation signals, you also have to authenticate the very precise arrival time of the signal. So you have to get right within a few nanoseconds when did the signal arrive. And it's possible to build spoofing devices that take the original satellite signal and delay it by a random amount and shift you elsewhere. It's rather difficult to prevent that sort of technique. There is one suggested technique that makes use of a property of the existing GPS satellite system, namely that if you don't know what the signal looks like, you can't actually receive it. The satellite signal is extremely weak. It's basically a light bulb worth of transmitter power at 25,000 kilometer altitude, and the only way you can receive that signal is by knowing in advance what it is, and then you use statistical tests to confirm, yes, I have actually found the signal where I expected it. if you design the signal such that you don't tell people in advance what it looks like, you just send out a random signal, no one can receive it, then a couple of seconds later you reveal what was the signal that you broadcast, and then everyone can go back in their recorded data and search for it and find it. Then what a spoofer who modifies a signal that comes down from the satellite only can do is they would have to delay that signal by a couple of seconds. And a delay of a couple of seconds you can easily detect by just having a local clock that, say, once a week you resynchronize over the internet. So that's one of the 2 or 3 different approaches that are at the moment being discussed, what can go into next generation GPS satellite system. And it's not just GPS. Europe is at the moment launching a system. The Russians have already a system. There's a Chinese system under deployment. So we will soon have 3 or 4 different operational constellations of satellites.
So in the future, the key to making these systems secure will be to make them unpredictable so you can't synthesize these signals. Thanks, Marcus. That was Marcus Kuhn from the Computer Laboratory at the University of Cambridge.
Also with us this week is Ramsey Farragher from the Digital Technology Group at Cambridge University. He's trying to make it possible to locate where people are in a room or a building with very high precision. So how do we locate people in buildings at the moment, or how are we trying to do that?
So there's a couple of standard schemes. One of them would be to deploy fixed infrastructure specifically in the environment, which costs a lot of money, putting beacons in the environment and giving people special receivers that they can go around with and be positioned by. A much cheaper scheme is to use things that are already pervasive in the environment, and that's what I'm looking at. So, for example, as I move through a given building, I can tell the difference between different rooms because I can see the colours of the wallpaper and pictures and the size and shape of the rooms. A smartphone can do a very similar thing in radio eyes and magnetic eyes, and a smartphone can learn what different rooms look like by the different signal strengths in the radio and different magnetic patterns. And what I work on is a way of making a device learn about the building and learn about what all the rooms look like, so that when you come back, you can very accurately locate where you've been in that building.
So you, as the holder of the smartphone, would be able to localise where you are and where you have been. What about turning it round and the building knowing where you are? I could see that be useful in situations like, for instance, fires or even patient care in a hospital.
Yeah, so that's certainly very possible too. So a way of doing that is that you choose to transmit the data that you're working out to someone so they can know where you are. But certainly there are things that you can do to allow an infrastructure in an environment to work out where people are. So a typical example is you put receivers through the environment, and when someone is texting or on the internet, on their phone, or they're making a phone call, the receivers through the environment can pick up these signals and work out the time difference of arrival of all the different signals. So they can effectively work out who you're closest to as you move through the environment. And very similar to the techniques we've just been discussing about GPS, given some receivers spread through the environment, you can work out where the transmitter is, the person who's texting or calling as they move through the environment. You can work out their position as they move through the environment by receiving the data from them.
It sounds actually quite a simple problem to surmount, but the fact that we're not doing this means there must be some wrinkles. So what are the wrinkles? So
it's certainly a very simple problem when the world is a nice, perfect sphere and you're in a vacuum and all that kind of stuff. The problem is in an indoor environment is extremely complicated. The metal in environments, the effect of signals going through walls, all this kind of stuff. And the technique that I'm working on, where the system learns what the environment looks like as it moves around, actually flips the whole problem on its head. The more complicated the signal environment, the nastier it is, the more unpredictable the nature of the signals, the better the positioning. And instead of trying to model and predict and work out what the signal should look like in a given place, you just record what it looked like when you were there, record all of these patterns, all of these signals, and you piece together what that environment must look like and what this really complicated pattern of radio and magnetic fingerprints looks like.
That, though, requires the device to slowly build up a picture of its world it's living in. What about the first time you go into a novel environment? It's not going to know anything then, is it? So how will it acquire that information or give meaningful information to start with?
Sure. This is the kind of key of the whole system. You have some way of estimating your motion around the environment. So the typical one we use is a modern smartphone is full of sensors, accelerometers, gyroscopes, a magnetic compass, a barometer. They're designed for gaming and making your screen rotate when you turn the phone round. In actual fact, you can do a really good job of tracking a user through an environment as they move. So I walk along with my phone held out in front of me, and the shaking that goes on in the phone, my software can recognise that and infer that I'm walking. And it can use the gyro-smoothed compass to infer a heading that I'm walking along. And using that technique, you can get a good estimate as a person as they move around a building. The problem is the errors accumulate with that system. So if I walk 100 metres, I might have a 2-metre error. If I walk a kilometre, I might have a 25-metre error. And the more I move around in my building, the worse it gets. But it's good enough to start piecing all these fingerprints together. And what the system basically does is it recognises when it's come back to a place it's been before, and it sees a sequence of fingerprints that match the past, and it can observe a correction that it needs to drive through the system, and it corrects its current position estimate and the journey as to how you got there. It effectively keeps tidying itself up, and the longer you operate in a building, or if multiple people move through a building and they can all share data, then you can very quickly build up these maps. The clever bit then comes when you've got a good enough map to turn off all of these sensors and just use the radio and the magnetic fingerprints, which is a much cheaper, battery life-wise, way of navigating around an environment.
So that tells me where I am in a building. How could we actually use knowledge of that data?
Indoor location-based services is currently estimated to be worth billions of dollars, just from the consumer point of view of things like pushing location-specific adverts to people. There's an interest in the ability to do things like target a text message or a push notification to somebody who's in a rival store to your store, and they might be looking at classic CDs in some shop, and you can push them this targeted little advert that says, I see you're currently looking at the classics section in that store. If you come to my store, here's a £5 gift voucher. It's valid for an hour, and here is the route from where you're stood right now to where my shop is. And that's worth a lot of money. And beyond adverts and the consumer stuff, the emergency services would love this kind of capability, not only so that when I make an emergency call, they know exactly where I am inside a building to the floor and the room, never mind just the building I'm in, but also tracking the emergency services themselves, the safety and security of firemen moving through a building, knowing that outside in the fire truck, someone is watching them move through that environment and knows to the room where they are. It's a huge safety line. And of course, from the military sector as too, looking after soldiers moving through environments as well.
It sounds pretty intrusive, though, but I can see why this would be valuable from if we were sort of designing an office or designing a public place and we wanted to see how the average person moved through it. You could achieve much better formatting in order to safeguard people's route through it. If it's a minefield, taking your military analogy, or if it's just an office, finding your way from the kitchen to the photocopier to cut down sort of wasted time, or maximise contact with people so you're more likely to have interactions that are meaningful in the workplace, that kind of thing.
Yeah, I mean, it's certainly only intrusive, of course, if you've not chosen to take part in this. But the whole point is I'm taking GPS that we love and depend upon, this life-saving technology, and moving it into the indoor environment so we can still benefit from all of those kind of capabilities. I'm sure you've been in a supermarket at some point, trudging up and down the aisles, wondering where the hell the beans are or whatever. You know, the capability to fire up your phone and do sat-nav at the shelving level in a big supermarket is something that everyone would opt into.
Undoubtedly, where can I buy shares? I mean, is this actually good to go? Have you got this system written, or are you at the stage where you've got the bare bones of this and you're beginning to see it implemented or do trials? Where's it at?
This runs live right now on my phone. I'm working on smartphone applications to do this kind of stuff. One of the fantastic things about smartphones is the sheer pace at which they're improving, and the kind of approaches I use and the kind of levels of software and machine learning that goes on. 10 years ago, you would have needed a desktop computer that was quite an expensive one. Nowadays, you can deploy it all on a smartphone and do it all live on a smartphone. And it's only improving the number of cores on the phones, the number of sensors in the phones. So it's a great time to work on this kind of stuff. And it's real time and ready to go right now.
The only obstacle, Ramsey, is the size of your wallet, I think, to sustain this. Thank you very much for a really amazing update on that. Ramsey Farragher, he is from the Digital Technology Group at the University of Cambridge.
Are you looking forward to GPS sat-nav systems with increased accuracy, or do you perhaps hate the idea of people knowing where you are within a shop? We'd love to hear your views. Email us here at chris@thenakedscientist.com. You can tweet at Naked Scientists or find us on Facebook.
This is The Naked Scientist with me, Chris Smith, and with Dominic Ford.
GPS might be best known as a navigation system, but researchers have also found it's a very powerful tool to measure environmental changes on Earth. We're joined by Christine Larson from the University of Colorado, who's developed a novel way to use GPS detectors to monitor volcanic plumes such as the ash cloud which grounded flights across Europe when the Icelandic volcano erupted in 2010. Now, Christine, how do people traditionally monitor ash clouds coming out of volcanoes?
I think it's a little bit like the way we think about monitoring weather storms. They use satellite imagery. You'll see the photos of the plumes moving, and that works fine if the weather's good and you have a good satellite image. But, of course, you don't have those images all the time, depending on the cloud situation. And another powerful tool for studying plumes is radars. And the problem with that is just you don't have radars where you have volcanoes. So you have to really be lucky and have the equipment you need to study that plume. And we just don't have enough equipment around all the active volcanoes in the world.
Now, you've been working with GPS sensors around these volcanoes. First of all, why were those sensors put there in the first place?
Right now, I've been working on data from Alaskan volcanoes, and those were put there by colleagues of mine at the University of Alaska and the Alaska Volcano Observatory. And they were using GPS in what I would call the traditional sense. I realize your last couple of people you interviewed talked about the real-time navigation you think of when you think about using GPS in your phone or in your car. But there's a lot of people in my business, which is science, that use it to study how the ground deforms. And we use these to very accurately monitor, in the case of a volcano, whether there's an eruption likely to occur, because before an eruption, the ground starts to inflate. The magma chamber inside the Earth starts to inflate, and that causes the ground to move. You have to have very precise GPS receivers to do that. So I had colleagues that had put GPS receivers there for a completely different purpose. They were going to measure the magma chamber inflating. And I just recently had the idea of seeing if we could see the plume by looking at the data from a different vantage point.
So how can that data from those sensors tell you about ash, which is actually in the atmosphere above those sensors?
Right. I mean, you have to look at things backwards. And I want to credit my colleagues at the University of Alaska. They had noticed that they thought they could see the effect of a plume on their positioning data. So they were measuring latitude, longitude, and height, and they noticed that during the eruption, the ground moved a lot. Well, that's not too surprising. You think, oh, an eruption causes the ground to move. Well, they were 5 or 6 kilometers away, and the ground should not have moved as much as it did. And so they correctly hypothesized that the plume was making the GPS positions wrong, just because it was an error that was unaccounted for when they calculated position. So they had first seen this, but when I looked at the data, I just said, well, you know, calculating position and then inferring that there was an eruption because the positions look bad sort of seemed like a difficult way to look at the problem. So I sort of looked at it differently and said, if I were a GPS signal traveling through an ash cloud, that would cause the signal to be reflected around. It, not as much as the signal would get to my antenna because it would be, if you will, distracted by all these particles, these ash particles. GPS was not meant to work in ash plumes. And so I hypothesized that that would cause the signal power to go down. So instead of looking at the positioning data, which is what all the rest of us use GPS for, I looked at the signal strength data, and that doesn't tell you anything about position. It really only tells you how good your reception is, just the same way, you know, your cell phone tells you how good your reception is too. So I looked at the signal power, and I could very clearly see when there was a plume.
So you got this sensor on the ground, and it's hooked up to various satellites in the sky.
Right.
And by seeing the signal strengths for those various satellites, you can predict what that roughly ought to be, I guess. If that's less than you expect, then you know there must be something in the way, so you infer there's a ash cloud there.
That's right, because, you know, these satellites, as you all know, they run, 24 hours a day, 365 days a year. Signal strength does not change. You know, the military runs them at specifications. And so I compared it to the day when there was an eruption, and I noticed the signal powers were perfectly fine in most directions, i.e. the directions that didn't go through the plume. So it turned out only 2 or 3 satellites were being affected by the plume. So that told me where the plume was. And if I made certain assumptions about where the volcano was, which we know where it was, or at least I looked on Wikipedia and found out where it was, you could infer how high the plume was and things like that. Because we know where the satellites are. One of your previous speakers talked about that. We know where they are, and that tells us which satellite's affected by the plume.
And am I right in thinking this isn't just about ash? You've actually managed to measure snow and vegetation as well.
That's exactly right. But I do it a little bit differently. So in the case of the volcano, I look at to see if signal strength has been degraded, if you will, less signal getting to my antenna because of the ash that is basically disrupting the signal transmission. To measure snow, what I do is, again, I sort of look at a normal day when there is no snow. I look at the effect of GPS signals that bounce on the ground and reflect back up to my antenna. Well, that has a very characteristic frequency. And then I compare it to a day when there is snow, and the reflected signal has a different frequency then because there's this snow layer. So I basically look at the patterns of reflections to tell me whether if the ground is moved. And if there's snow on the ground, that makes it look like the ground is higher. And then when the snow melts, it gets back to where it originally started. And similarly, if there's vegetation on the ground, that changes the bounces off the ground as well. But it's all using signal strength data, and it's all using the same equipment that other people use to measure latitude, longitude, and elevation.
At the moment, it sounds like you're using arrays of sensors which have been put down for other purposes, for looking at ground movements. But given how much you're managing to infer from this, it sounds like it might be worth building arrays in areas where you're interested in monitoring snow and vegetation and so forth.
That's exactly what we're going to try to do. Since we are doing something pretty simple, we're trying to make the GPS sensors cheaper because, for example, the reason we all have GPS sensors in our phone is because people have come up with very cheap GPS sensors to use there. For the kind of thing I'm talking about, I think we could do the same thing. So what we'd like to do is we've shown that you can use these GPS receivers that were put out to measure plate motions and volcanic motions. We've shown you can measure snow with that, like you said. But we'd like to do it in arrays with cheaper sensors, and that's what we're working on. I have some students working on that and some colleagues working on that so that we can provide a cheaper environmental sensor.
Well, thanks very much, Christine. I'm sure that's something we'll be keeping an eye on in months ahead. That was Christine Larson from the University of Colorado.
And sticking with the geological theme, finally, Hannah has been moving mountains for us to try and answer our question of the week.
This week, we cast our eyes to the skyline to try to answer a question that Eugenie Podolsky wrote in with.
So I am just wondering, how high could a mountain on Earth be? The Olympus volcano on Mars is about 20 kilometres high. But could a peak on Earth ever reach this height? And if not, why?
So, how do mountains form, and what's to stop them reaching further up into the sky?
My name is Nicky White, and I'm a geologist who works at the Department of Earth Sciences in the University of Cambridge. It's well known that the Himalayas are amongst the highest mountains on Earth, with Mount Everest peaking at just over 8 kilometres. And an important question is, why on Earth do you not get mountains that are higher than that? And the main reason is that there are two things fighting against each other when you make mountains. First of all, you have the plate forces. So for the Himalayas, India is colliding with the Eurasian plate and forcing the crust to become thicker, which pushes the Himalayas up in the air. But something else is going on that's often not talked much about, which is that mountains eventually tend to fall down just through their own weight. And the important concept here is something called viscosity, which, if you like, is the runniness of the rock that's inside the mountains. A useful analogy is something like syrup. So if you imagined that you created the Himalayas out of syrup, I think it would be easy to see that as soon as you start pushing the mountain up in the air, it also starts to fall down because the syrup will flow out sideways. And it's just the same in the Earth. So rocks are not quite as runny as syrup, but they still have a certain ability to flow. So it means when you build a very large mountain chain, as soon as you start to reach a certain height, it will begin to fall down under its own weight. So the Himalayan chain is actually beginning to squirt out sideways, mostly towards China, which means we're probably at the limit of of the maximum possible elevation achievable on Earth. On other planets, such as Venus and Mars, the viscosity of the rocks may be different, which is why you can achieve higher mountains.
Thanks, Nikki. So mountains fall down due to their own weight, and the height at which they start to fall is due to how runny the material is that they're made up from. There's actually a number called the Argon number, which is essentially the weight of the mountain divided by its runniness, and this helps us to know how high a mountain can grow. Everest is just about at its max. We now turn our pondering eyes inwards as we try to tackle our next question.
Hello, my name is Klaus, I'm from Sweden. What is the physiology behind emotional breakdown? Everybody has had the feeling in traumatic situations of getting all choked up, voice breaking and tears welling up. What is happening in our bodies during such occurrences?
So what is going on in our bodies and brains during an emotional breakdown? Send your thoughts to studio@thenakedscientists.com. You can tweet @nakedscientists. You can write on our Facebook page, or you can join in the live debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow.
And that's it for this week. Thank you to our guests, Marcus Kuhn, Ramsey Farragher and Christine Larson. Thank you to Dominic Ford for joining me. Thank you, Dominic. And the production this week, thank you, Kate Lamble. Next week, we're going to be looking at the heights of Everest and the depths of the ocean to discover the physiology behind how humans survive in extreme environments. The Naked Scientists comes to you from Cambridge University. It's supported by the Wellcome Trust and the EPSRC. My name is Chris Smith, and thank you for listening. Goodbye.